In this video, we will see thermal expansion stresses. The first case is free expansion. Here in free expansion, we do not restrict any expansion of due to the thermal. So here you see there is a cantilever beam and we are increasing the temperature by delta T. So material property is Young's modulus E and thermal expansion coefficient alpha. The length is L. Now if you see delta L T means thermal expansion, change in length due to thermal expansion. It is given by alpha L delta T. Alpha L is the length and delta T is at increasing in temperature. If it is decreasing in temperature, then delta T will be negative and delta L will be in negative direction. Thermal strain is alpha delta T because delta L by L is alpha delta T, so thermal strain. And here there is no thermal stress because we are not restricting by any obstruction. It is freely allowing to expand in this direction. This red is the expansion of length after expansion, so L plus delta L. So there is no restriction, that's why there is no thermal stress. The second case is complete restriction. So we put a wall on the other side also. So in expansion or contraction there is a load generated because it is thoroughly joined on the edge. So in expansion, if the material expands, wall will try to compress, so there will be compressive load on this cantilever beam. So this is the free body diagram. Now if it is contracting, when we decrease the temperature, so in expansion compressive load because we are increasing the temperature. In contraction, where we decrease the temperature, the material will contract and there will be tensile load on the material. So because wall is sticked here, it is joined completely like a welding, so wall will try to hold it and material try to contract, so there will be tensile load on this material. Now if you see here, when expansion is there, compressive load; when contraction is the tensile load. So here delta L will be alpha L delta T, but the direction means positive and negative depends on whether it is tensile or compressive. So in compressive, thermal stress will be positive like the free expansion case. So thermal delta L due to thermal will be equal to alpha L delta T only, but now this expansion we are restricting. So when we restrict it, the total delta L will be 0. This is a 0. But if you see thermal plus mechanical is the external load which is generated. So here delta L thermal is this much, delta L mechanical is due to this external load, and the total expansion will be 0 because this final case it is not changing its length. So delta L thermal, which is alpha L delta T, plus mechanical, which is PL by AE. So in for expansion case, PL by E is negative because there is a compressive load. So due to this P, there will be change in length again. So due to thermal strain, it is expanding. Due to external load P, it is contracting. So overall, it is 0. When it is in contraction, so thermal stress is negative, but due to this tensile load will be positive, PL by E. So again, here it will be negative in a contraction case, and here it will be positive in contraction case. So at the end it will be 0 only. So now if you see stress, so stress will be equal to load generated, which is P divided by area. And if you see in terms of strain, so alpha E delta T, strain is alpha delta T, and if you multiply by Young modulus, then the stress will be equal to alpha E delta T. Plus minus is due to expansion and contraction. So when it is compressive, it will be negative; when it is in tensile, it will be positive. So the next case is partially restricted. So here we are not fully restricting, we are allowing it to expand up to some point, and then we further increase the temperature, then there will be this completely restricted case. So here free expansion till this gap y is filled, and that is the maximum possible expansion. And then after increase in stress but no expansion. So after that there is a increasing in stress and there will be no further expansion, and there will be expansion due to thermal energy, but that will be completely restricted by the force which is generated due to this wall. So again delta L T thermal plus mechanical will be equal to 0. So alpha L delta T will occur, but wall will generate compressive force and PL by A will also occur. So here P will come as negative if we are finding it. So I have shown it positive here, but it inside this P value will be like some minus times some Newton. So minus 10, minus 20 like that inside here. I have shown here externally. Here P will be positive, but here the sign of this P will be negative. So in this case, load will start increasing after the gap will filled, which is Y. So delta L total will be Y, which will be equal to delta L thermal, which is more than delta L mechanical, because delta L thermal is total expansion due to thermal. Now restriction is only up to this wall. This will be the free expansion. So free expansion plus the load will be equal to total thermal. So PL by E. So load will be less as compared to this completely restricted case, because we are allowing up to certain point. And in contraction also this will holds true, because P and alpha L delta T sign will change. So uh, this case is valid for both. This is a general equation for both the cases. In the next case, if you see compound bars, so we have two materials, alpha 1 alpha 2 e1 e2. So these both two, blue color and black color, both are joined parallelly, and alpha 1 is greater than alpha 2, so expansion of 1 will be more. So now if you see here, this blue color will expand till here because its alpha is more. Black color will expand till here if they are expanded separately, but both these are joined together. That's why they both will expand up to this point. So both will expand equally. So this blue color supposed to be expand up to this point, but this black color will pull it till this point. So it will expand till this point. There will be load generated which is equal to some P value in blue. It will be compressive in nature. Here this black color is supposed to expand up to this point, but this blue color will pull it on this direction. Tensile force will generate and it will come to this position. So both will expand till this position. Blue will will be having compressive stress and it will come to here. Black is having tensile stress, it will come up to here. Now if you see, the total thermal expansion of the blue separately will be alpha LT1. The total thermal expansion of 2 will be delta LT2. So total thermal means thermal only. Now, due to the mechanical stress, which is P value, which will be equal in both, here P is tensile, here P is compressive, because both are action reaction. So due to this P, it increased by this much, which is delta L mechanical 2, and due to this compressive P, it is contracted here, means compressed till this point, which is delta L mechanical 1. So if you see here length, this total delta LT1 will be equal to sum of these three, this plus this plus this. So delta L thermal 1, which will be equal to delta L thermal 2 plus delta L thermal so delta L mechanical 1 plus delta L mechanical 2. So here thermal total will be alpha 1 L delta T. We are increasing both these materials simultaneously at a delta T, and length is same for both, equal to delta LT2 will be alpha 2 L delta T, and mechanical is PL by A1 A E1. We are assuming cross section is same, and E1 is the Young's modulus of 1 plus PL by A E2. E2 is Young's modulus of 2. So this is the equation which is come by this complementary equation and summation of this delta L. So these are some basic cases which are asked in major examinations, specifically in gate examination, and also this particular question, compound bar, is recently asked in ISRO interview. And so prepare these cases and solve some numericals for this. Thank you for watching this video, and see you in the next video.